Okay, this video is covering a Huffman coding example that I want you to be familiar with and know how to do. And like many things that we do, it's a really simple model. It's not practical. You don't see source alphabets with just 3 letters, okay? But we're going to start with something that has 3 letters, and we're going to make a probability assignment on those 3 letters. Now, normally our message alphabet, like with English language, we have 26 letters, not counting, capital and lower cases and punctuation and all those kind of things. So normally an alphabet is much bigger than just 3 letters, okay? But we're gonna have just 3 letters, and the probability of letter A is 0.7, probability of B is 0.2, and probability of C is 0.1. All right, so the first thing I want you to be able to do is calculate the entropy for this particular alphabet. And we go through these calculations. We put in that log times probability. So log of 0.7, log base 2 of 0.7 times 0.7, log base 2 of 0.2 times 0.2, log base 2 of 0.1 times 0.1. There's a minus sign out in front of everything. And we end up calculating that to get 1.1568 bits. All right, so the next thing I want you to do here is be able to assign a Huffman code to U. All right, so let me review what I'm doing here. What I do is let me just start from scratch and reproduce this step by step. Okay, so what I do is I make a little tree here, and I assign the probabilities at each sort of node in the tree. So 0.7, 0.2, 0.1. All right. From here, the tree is formed by grouping least likely pairs. Okay, so 0.2 and 0.1 are less likely than 0.7. Okay, when you add these probabilities together, you get 0.3. Then there's only one pair left, 0.7 and 0.3. You add those together to get 1. Your last grouping should always add up to 1 because that's what probabilities do. All the sum over the whole space adds up to 1. Okay, from there, we can assign a way of encoding the tree. Now, if we label both the upper and lower branches the same way, we're guaranteed to get something called a prefix code. We'll talk more about that in a different video. Okay, so upper is 0, lower is 1, upper is 0, lower is 1. Then we read backwards. All right, so I'm going to read through here. To get from the trunk of the tree back to A, I go through only the single bit 0. Okay, on these other ones, let me change this to red. If I go from the trunk of the tree back to B, I go through 1 and 0. So that code word would be 1, 0. And finally, to get to C, I start at the base and I trace my way to C, and I go through 1, 1. All right, so that's a Huffman code for this very simple case. All right, from there we can calculate the average value of the code. All right, so the average, when I say average value, I mean the average code length for each of the code words. Okay, so in the case of the letter A, the length is 1, right? There's only a single bit, and the probability is 0.7. So 1 times 0.7 gives me the expected length of the code that represents letter A. All right, repeating that for B, 0.2 times the length of that code is 2, and for C, 0.1 is the probability and 2 is the length. So I calculate that, add those all up, I get 1.3. This lets me then calculate the efficiency of the code. All right, so the efficiency is just the ratio between the entropy of the code and the average code length. All right, so I do that calculation and I get that this is an 88.9% efficient encoding for this alphabet. All right, so the next thing I wanted to do is show you that you can actually keep getting this closer and closer under certain simplifying assumptions, closer and closer to the entropy bound. And the assumptions are that we have independent probabilities. That would be a really questionable assumption in practice because, for example, English letter language letters are not independent, right? For example, the most extreme example, if I get a Q, I know that my next letter is most likely going to be a U, all right? They're not independent. Okay, but under this assumption, we can extend this code, and the way we do that is just like I'm sorry, fumbling over my words here, but we take each letter combination and figure out all the possible pairs, okay? So I could send an AA, I could send another possibility would be A and B, and then A and C, and you see, we list out all possible combinations of 2 letters from a 3-letter source. Okay? So from that, we can calculate probabilities. So we're assuming these probabilities are independent. So I know that the probability of letter A is 0.7. 0.7 times 0.7 gives me this first number, 0.49. All right, then the probability of letter B is 0.2. So 0.7 times 0.2 is 0.14. Probability of C is 0.1. So 0.7 times 0.1 is 0.07. And so forth down the list. You can list all the probabilities of each pair of letters. Okay, so the last one, the probability of C is 0.1. 0.1 times 0.1 is 0.01. All right, so there we go. We got the first step done on extending the code. Now we're making a Huffman assignment by drawing this code tree. All right, so the way we did that before was we looked for the least likely pairs. Okay, so looking through my list, I see 0.02. Actually, I see it twice. I'm just randomly choosing one. And by the way, there's several procedures that if you look up Huffman encoding, you can do a more complicated procedure that will give you the same average length code, but the variance in the length is smaller. Okay, that requires re-ranking at every stage of encoding. And that's not the point here. The point here is just to show you that you can get to a more efficient code by extending the code. So I'm not going to do this re-ranking business. I'm just looking for the least likely pairs. Okay, so I see 0.02 and 0.01. Combine those together with a tree and add that to get 0.03. All right, then I'm looking for a different pair. All right, so I'm looking at my list. My possible lists are 0.03, 0.07, 0.02, 0.04, 0.14, on up the list. I'm looking for the least likely pairs. Okay, and so I find it at 0.03 and 0.02. All right, that's the least likely pair. And so I combine those together to get 0.05. Okay, now I'm doing this again at this next stage. I don't need to look at these prior probabilities moving back to the left because I've already represented this. This 0.05 already has this path and this path taken into account. And the 0.03 already has this path and this path taken into account. So I'm just looking at the outermost branches of the tree up to that point to combine these into pairs. All right. So I'm saying 0.05, and then I see from this list 0.04. So I select those together, these two together, to get a probability of 0.09. Okay. And I keep doing that. I see 0.09 combining with, I see 0.07. Let me get a different color. Let's go orange. 0.07 combining here. Those two 0.07s are less than the 0.09, so the 0.09 didn't get combined at that stage. 0.07 combined twice gives me 0.14. Okay, and so now I'm looking at my list and I'm seeing yet a different color. 0.09 combined with 0.14. It's a tie, right? I can take either path, but this gives me a little cleaner look. Okay, and that combines together to be 0.23. All right. Now 0.23 is bigger than 0.14, so I see a couple of 0.14s on the list here. So let's combine these two together. Okay. And so those two 0.14s combine to a 0.28, and then the 0.28 and the 0.23 combine to give me the 0.51, and the 0.51 combines with the 0.49 to give me 1.0. Okay, so this is the Huffman encoding tree, and now to read back the code, you just need to assign bits to the branches, all right? And so if we do that in a consistent way, we get a prefix code. So let's do, what did I do before? I did 0 on top. I could do 1 on top. I want to show you that you can do it both ways. 1 on top, 0 on bottom for every branch. Okay. All right, so it looks like I got them all. Okay, so our next task is to read our way back to every pair of letters. Okay, so when I read my way back to AA, I get here, I'll follow this track back. I only go through a single bit, so that would decode or encode to a 1. All right, so I'll take a different color, trace my way back to AB, and it looks like I run through a 0 first, and then a 1, and then another 1. Okay, and then I do the same thing all the way back through, and I have, I'm looking for AC. Here's the path to AC. Okay, so for AC, I run through a 0, and then another 0, and then a 1, and another 1. All right, so there's AC. All right, so I'm going to pause the video here and calculate the rest of those, and then we'll jump back into it. Okay, jumping back in this, I went ahead and finished all of the tracing back through the tree and came up with the code words, so you can check these yourself. But for example, the combination BC ends up with the code word 00001. Okay, so that makes this harder to read. So, but you get the idea. You trace it all back. When I go through this calculation, I can then calculate in bar the average number of bits from this column. But then keep in mind, I'm taking these 2 letters at a time, so I need to divide the average number of bits by 2. Okay, so if I take that average, I get 2.33. All right, I'm sorry, 2.3. And the way I come up with that average is I take each value. Okay, so that's one bit long times 0.49, 3 times 0.14, 4, because it's 4 bits long, times 0.07, 3 times 0.14. Go through the whole calculation there, and you get 2.3 bits coming out of that, and then you need to divide that by 2 to get the number of bits per letter. And so it works out to be 1.165 bits per letter, all right? And so you compare that to h of u. H of u was 1.1568. All right, we can come up with the efficiency in that case by dividing by in bar over L, where L is the number of letters. Okay, and so that would be 1.165. And let's see, 1.1568 divided by 1.165 165, and we get 99.3% efficiency with this code. If we wanted 99.9% efficiency, we could keep extending this, and every time you extend it, it grows exponentially, and so it gets to be really tedious, but you can get as efficient of a code as close to that n bar as you want under these simplifying assumptions. Okay, so that doesn't quite finish what I wanted to cover. The next thing I wanted to cover is the idea of this being a prefix code. All right, so what I want to do here is talk about a specific code. All right, let's say we sent this combination of letters CC, AB, AC using the prefix code. Okay, so had we joined this with two letters at a time, we're looking at CC, AB, AC. So I look at CC and I get 6 zeros, 1, 2, 3, 4, 5, 6. I look at AB and I get 0, 1, 1. Okay, then I look at AC. AC is here, 0, 0, 1, 1. All right, and I realize this is going to be the message that I get, and now I need to be able to decode that. All right, so as I'm going through this, I take this bit at a time. All right, so this is what it means to be prefix. I look at bit 0, okay, and I go through my code word list. Let me move this where we can see it all at once. Do I see anything, any code word that is a 0? All right, so here's my whole list. Let me clean it up a little bit. This is my list. I take this bit at a time to decode. All right, so I look at that 0. There's nothing in there that's just a single 0. So I go ahead and I add the second 0. Is there a code word that is 0, 0? No, there's not. I keep going. Nothing that's 3 zeros. Nothing that's 4 zeros in a row. That doesn't, 4 zeros doesn't appear in this list. 4 zeros with a 1 does, but that's not, I haven't reached that full code word yet. Okay, and so I keep going, and finally, when I get to the 6th 0, there's a code word. All right, so as soon as I see that, I can write down CC. All right, then I start over. 0, that's not on the list. 0, 1 is not on the list. 0, 1, 1, that's on the list. That's code word AB. All right, starting again. 0 is not on the list. Not in this list right here. Okay, 0, 0 by itself is not in the list. 0, 0, 1 by itself is not on the list. But 0, 1, 1, that shows up here. That is AC. So I think you would see it'd be really a problem to decode this if we didn't generate what's known as prefix codes, where no code word shows up at the front end of any other code word. Because if it was not a prefix code, it'd be really hard to debug that or to decode that. Okay, so that's what I wanted to show you with this video. I'm going to give you a homework assignment that lets you practice this process of doing Huffman coding so you will develop a feel of how you come up with an efficient way to represent a source.